really, completely blasting through the amount of the amount of impact that we can so far make in terms of postponing the health problems of late life in mice. At the moment, we can get 4 months. If we take mice that normally live 2.5 years, and you start doing things to them in middle age, so when they're 1.5 years old, the best we can do is about 4 months of um, life extension. And we got pretty much that in this experiment that we've just finished or almost finished. So we've done about as well as other people have done in the past. But the really shocking thing, which very few people even mention, is that we could already get those 4 months 50 years ago. I mean, a very, very long time ago. It is, it's a real testament to our lack of progress that no progress has been made. And I'm very sure that the reason no progress has been made is because we spent all this time messing around with metabolism and just, inducing calorie restriction responses, things like that. And we haven't done damage repair. And so now all we need, I believe, is to get a sufficiently comprehensive panel of damage repair interventions put together in the same mice at the same time, and we will get more. I've given a kind of a goal, a milestone that we want to achieve, which is to get 12 months of additional life rather than only 4 months, so trebling the effect size. But I think even if we doubled the effect size, that would be just completely mind-blowing. And not only that, it would be mind-blowing for the whole field, for all of the expert community. And that's what I'm really focused on, because the expert community are the people who define what happens next, what happens in society, what happens in terms of public policy, and so on. And of course, what happens in terms of the effort, the actual amount of resources that are put into having a proper war on aging. So that's my goal, to make a war on aging happen as soon as possible. And I believe that the way to do it is to get middle-aged mice to live a lot longer than they do at the moment.
Okay. So, speaking in terms of style, you said that Brian was a bit of a weirdo, Brian Johnson, and I suppose he is.
I didn't say he's a weirdo. I said that he is perceived by a lot of people as a weirdo. I don't think he's particularly weird at all.
Well, I think it's good to be weird in some sense, and he's quite a unique character, shall we say? You're a bit
I
of a
certainly
unique
don't.
character as well.
Yeah. I mean, I think yes, it's certainly pointless to be normal. I'm all over that. I think, the connotation of the word weirdo is a little bit different from the connotation of weird. So that's all I was trying
But you
to
said it in
emphasize. Yeah,
a
I mean,
tongue-in-cheek manner.
right,
Some people
exactly.
compared him to a lich or a vampire, but he's doing this blood transfusion with his son and all these weird things. Would you say that your approach, I have to ask, do you have the beard? Is that like a Gandalf the Grey reference?
I had the beard before I became prominent. I grew my beard because my first wife was a fan of beards. So no, there's no actual reason. It has become a bit of a trademark, of course, but I don't have it for effect.
What do you think about the idea of this hair turns grey over time? They're working on reversing that. I read something David Sinclair was posting about that. Is that coming? Is
Yeah,
that
so this is not all that new. I mean, of course, there are incremental breakthroughs in the details and making it easier to do, making it quicker and so on. But yeah, I mean, we have known for a long time that the reason hair goes grey is because of the death of a particular type of cell in the skin called a melanocyte, which makes melanin, which is the pigment in the hair. Um, so of course these cells are regenerated periodically. If the skin is in a regenerative state, the skin does that. And so it's kind of no surprise that hair can be made no longer grey by regenerative rejuvenation treatments of various types.
What about the brain? Because people ask about the aging of the brain, and on some level, there's maybe no difference between the brain and the rest of the organs. But I don't know. The brain is so complicated, and people's minds are just so. I don't know.
Well, okay. So I guess there are two big answers to that. The first thing is you're absolutely right. The brain is made of the same stuff as the rest of the body. It's made of, cells and stuff between cells, and the cells are made of the same stuff and so on. Um, of course, functionally, the brain is ridiculously complicated. But this is something that really defined my whole approach to combating aging right from the beginning of my career switch from artificial intelligence research. That, we have to recognize that we don't need to understand everything about a system in order to manipulate it. We just need to understand enough. And then the best of it is that enough depends on not on necessarily how complicated the system is, but rather on our goals. And here we need to remember that we are working with the body. In other words, the body already has a huge arsenal of, inbuilt automatic anti-aging machinery that keeps it going. It tries to keep itself going. And our goal is simply to augment that inbuilt machinery so that the body keeps going even better, which means that in the case of the brain, if we can do fairly, gross things like just, eliminating the waste products like amyloid plaques, for example, and maybe replacing some cells in, for example, the substantia nigra, which is where cell death causes Parkinson's disease, and such like. If we can do a few fairly simple things like that, um, then the brain will just figure out how to rejuvenate itself in all the ways that we don't understand, because it already has the wherewithal to do so. That's the philosophy that I've always followed, and it's very important to remember it.
Aging didn't exactly evolve to benefit the organism or its descendants, did it? It just sort of, the mechanisms of the body get so far and then it breaks down and fails, hopefully after the organism has already passed on its genes well enough and that sort of thing. So there isn't actually a benefit to getting old in the first place, really.
Right, exactly. But the reason we get old is because simply we get eaten and we starve to death and we freeze to death in the wild, which is where evolution happens, of course. And therefore, we have come to the point where um, we get sick when we get old simply because in the wild there are not enough of us around anymore when we're old that evolution can be bothered to fix it. Certainly, it would be better for any species not to have aging than to have it, but it wouldn't be sufficiently better to outweigh the rate at which, excuse me, the rate at which mutations occur in our genes that progressively degrade the machinery.
Is there anything that we are going to gain from species like the naked mole rat and the hydra and all these little things that live a very long time, like sharks and crocodiles?
Right. So it's very important to study other species and get clues from them. But the disappointing thing is that most species that look impressive at first sight turn out not to be very useful to us because in some way or other, if you like, their aging problem is less of a problem than our aging problem. So, for example, hydra and sea anemones and so on, they don't have brains. They don't have any cells, in fact, any organs that rely for their function on being made out of long-lived cells, whereas our brains and indeed our hearts very much do. That makes our problem much harder. Cell division is a very rejuvenating process. It dilutes damage and so on. And if cell division isn't happening in a given organ, then its problem of aging is much worse. Similarly for sharks, for example, or alligators. These are animals that live a nice long time, but they grow continuously throughout life. Lobsters are another one that's often cited. And the thing about continuous growth throughout adulthood is that, again, you've got constant cell division happening. Now, sometimes that cell division will not necessarily be to dilute damage. It may be to replace cells that have died because they've got too much damage. But it's still cell division, the machinery is there. Whereas in a species that has a fixed size in adulthood, like us, an organ like the brain, for example, simply loses the ability to create new neurons because because evolution can get away with simply keeping the existing neurons alive for a nice long time, but not forever. Then there are some cases which are very interesting, and we can get clues from. The naked mole rat is a particularly good one. So, for example, we've discovered the community has discovered that naked mole rats have an extremely clever way not to get cancer, which essentially involves making a very unusual form of a chemical called hyaluronic acid. And this is a big area of study right now. Other animals have done similar things, like elephants, for example, have a very large number of copies of a very important anti-cancer gene called P53. Um, the different species have done different things, and we can get clues from these things. Sometimes those clues may not actually be practically exploitable from a medical perspective. So, for example, birds live a lot longer than mammals of the same size in general. Of course, the naked mole rat is an exception. Um, and the way the birds do this in general is by having a very low rate of production of free radicals at their mitochondria. And we kind of understand at least a bit about how they do that, but turning that into an actual therapy would be very, very hard. It would involve, an impractical amount of replacement of genes, for example.
Right. Okay. What do you suspect will be the most difficult type of damage to clear?
I still don't really know, but um, the reason we don't know is because new ideas keep turning up. So, for example, 5 years ago, I would probably have said that eliminating mitochondrial mutations is the hardest. But now I'm beginning to think it might be a lot easier than I thought 5 years ago,
Why?
because we have some clues about how to selectively destroy mutant mitochondria in the cell by this process called mitophagy, in a manner that could be quite easy to trigger. Essentially, we know more now about what the signaling process is that causes the cell to destroy particular mitochondria. And essentially, what we might be able to do is a relatively simple way to tweak that mechanism, that signaling process, so that it's um, so that it pays more attention to mutant mitochondria and gets rid of them more easily. If we can do that, then we may not have to do any of the stuff that I have always thought we'd have to do, which was essentially to put the mitochondrial genome into the nucleus, which is a really, really hard thing to do. Something that we've made progress on over the years, but it's still a long way away. These are the kinds of things that happen. This is what engineering is all about. You keep looking for new ideas that are shortcuts to what you thought you were going to have to do.
Are we going to get things like, because your tongue, your taste buds sort of die off over time, and your eyes, your vision tends to go all more fuzzy, and you get cataracts, you get eye floaters, and that sort of thing. Are these things going to be cleared up as well?
Oh yeah, I mean, actually, the eye is a great example because on the one hand, it's it's on the outside, so you can get to it easily from a medical point of view. So that's nice. Also, the eye is pretty much entirely lacking in any kind of immune system, which means that you can do things there that you can't do elsewhere because of rejection or because of immune response. In particular, gene therapy. So there are various gene therapy clinical trials going on right now. Gene therapy is coming, but if you look at what those trials are for, the vast majority of them, as of now, are for ocular problems because you can just do gene therapy in the eye a lot more easily. Um, then things like cataracts or presbyopia or indeed glaucoma, these are things that are relatively easy because they involve macroscopic problems. Basically material that accumulates or crosslinks that accumulate. These are things where we have a respectable chance of being able to do genuine damage repair, genuine rejuvenation, with technology that might be rather more primitive than what we would need elsewhere in the body.
So one of the problems in living long enough to reach longevity, escape velocity, to live forever, as they would say, is if your life is not getting better, it's probably getting worse. And for some people, they end up just really depressed, or they end up having some financial catastrophe, or they end up killing themselves, or something like that. What do you think about antinatalism and depression and all these things? Is this getting solved as well?
Um,
Is there anything you
well,
can
you've
say?
asked two different questions there.
Yes.
So on the depression side, you know, this is very much not my field, but I completely agree with what you say. You know, a lot of people just get bored of life, or they get exhausted,
Or they
or
don't
whatever.
have a meaning in life. Like I think
Well,
that
that's
that's one of
right.
the most
Yeah,
important things, living long
yeah,
and healthy.
exactly, exactly. So, a lot of people, the only reason they have kids is in order to give themselves meaning in life.
And the birth
Um,
rates are going down as well. So
well,
people
that's
are,
right. You don't have to have
are
many kids to give yourself
and
meaning in life.
automation is taking jobs too. And some people derive meaning
Mhm.
from their jobs, and some people have something that they want to do that their job prohibits them from doing. Because work is, in
Yeah.
some sense, just what you do when you have to do something. But, you know,
Yeah, I'm completely with you on all of this. I think that we really need to put work into making life more fulfilling. However, maybe the only work that's really required there is to make it easier for people to spend more of their time fulfilling each other. I mean, ultimately, the single most fulfilling thing in life is feedback, right? It's knowing that you are enriching other people's lives.
connection
And
with others. Yeah.
yeah, that's right. Yeah. And a huge amount of the absence of that in today's society arises from the rat race, from simply not having enough time, or money, or both. Um, so, to the extent that we can fix that, whether automation will improve prosperity and so on, the chances are, to my mind, that we may be, on the road towards improving how fulfilling life is, just like that. But you
Exactly.
had a second part of your question. You had a second part of your question, which was about antinatalism. I did an actual podcast a couple of months ago,
I saw that.
um, which was called the Antinatalist Podcast or something like that. Um, and it's not an area that I've explored very much. I personally have never wanted kids, but that's because I guess it's largely because my life is already fulfilling, and I've always felt that the right thing for me to do was to spend my life, contributing to the humanity. And kids are a very time-consuming thing that a lot of other people are good at. So it's not the thing I wanted to do. But of course, there are other aspects of antinatalism that basically say, we have a moral obligation not to bring new potential for suffering into the world, things like that. And, I'm not honestly sure what I think about all that. I certainly would not consider myself a philosopher in any way at all. So I don't have a strong opinion there.
Some people might, what I call them is procrastinatalists. They just procrastinate on having children indefinitely. And, maybe once they have radical life extension, they might have kids when they're 50 or 70 or 100, who knows. But you might get some people who just have like just endless children, just have massive families, and that might be fun as well. And probably the carrying capacity of the planet would be fine for that as well, especially considering the birth rates are generally going down. But I feel like some people get into anti-aging as a way to just procrastinate on life itself. Carl Jung talks about the puer aeternus. He was a psychologist. And so some people, I wonder if even billionaires, the reason they don't invest in these things is because they're just sort of waiting for other people to do it for them. What do you think of that?
Yeah, I think there's plenty of truth in that. But I guess that's part of being fulfilling, isn't it? I mean, I mean, if we come back to what I was saying earlier about the most fulfilling thing in life being to enrich each other's lives, then, the way you enrich the way you enrich other people's lives is by doing stuff, right? And not procrastinating. Now, exactly what you do is, of course, a personal choice.
You
But,
have to live with a
um,
sense of urgency.
well, no, I don't think it's necessarily urgency per se. I think it's well, I mean, you could use it. I could use a negative term, peer pressure. That might be the same kind of thing, really. Um, that it's not as if some particular thing has to be done soon. and indeed, I don't think that um, most things that people do in their lives, they do because they've only got a certain amount of time to live. You could argue that having kids is an exception, that women will only delay having kids for a certain amount of time because they know they've only got a certain amount of time before menopause. Um, and as you say, the chances are, in my view, that when menopause becomes optional and or reversible, we will have less urgency to have kids, and therefore the rate of population growth globally may actually slow down.
And people have all sorts of anxieties about that sort of thing, like menopause and Ozymandias, and even the Epic of Gilgamesh talks about like stress of aging and just youth and that sort of thing. It's just, I think it causes people to make some bad life choices, like you reach to a partner that they're not maybe suited for, and then you have all this trauma that's intergenerational and such. What about bones? Like bones get weaker with time. Are you going to fix bones?
Bones are actually a relatively easy thing because even though bones look very static, they are constantly being remodeled. We have cells called osteoblasts and other cells called osteoclasts. And these cells, osteoclasts break bone down and osteoblasts build new bone. And that's happening all the time. And the way it works is essentially in response to physical stress and strain. The bones that are load bearing or that are being used in exercise and so on are the ones that the bone remodeling responds to that. So we do see one thing in bone, of course, that is a very important aspect of aging, namely loss of bone density. Um, and that's generally seen to be because of a change in the ratio of these two types of cell I just mentioned. You have fewer osteoblasts and a larger number of osteoclasts. And we have some pretty good understanding now of how that happens. Um, and there are definitely ways in which people are trying to fix it. Also, it's linked to other things. So, for example, there's one theory that says that the loss of bone density is a compensation in order, well, kind of trade-off in order to minimize the amount of deposition of calcium in places other than bone, especially in the artery, where it plays a role in atherosclerosis. So yeah, it's a complicated network of things, but bone is something that we probably don't have to go in and fix directly. It will fix itself as a consequence of fixing other things.
Hmm. Do you think that artificial intelligence is like the protein folding problem? How solved is that? Because I hear like all the time, oh, it's been solved, oh, it's been solved. Like I heard this a few years ago, and then later. Exactly how
Yeah.
solved is it?
Okay. So of course, when the first version of AlphaFold came out, it won this contest called CASP, which is a contest that had been going on for decades. Um, to use computers to predict protein structure, but it didn't win it by much. It was considered a sign of things to come. I mean, sure as hell was a sign of things to come because 2 years later, at the next competition, it completely blew the field away, and that was when people were saying, the whole thing is solved. Now, that was an exaggeration. It definitely was not completely solved then. Various proteins that are present in membranes were hard to do. We also wanted to have ways to predict the structure of protein complexes where you've got multiple different proteins interacting with each other, and then also proteins interacting with other molecules that are not proteins. They're ligands or they're cofactors or whatever. And progress has continued, of course. So now we have that was AlphaFold 2. Now AlphaFold 3 is on general release. It's open source. And I have not been keeping up with the literature on how much better it's getting, how much more rapid, how rapidly it's getting better. But I'm quite sure it's getting better all the time. And furthermore, that they've probably only released AlphaFold 3 because they've already got AlphaFold 4 in-house that's even better than that. Um, on top of all of that, and this is really the important thing to me, we have, as I think I mentioned already, a program now which derives from the same basis, of course, that does the opposite, rather than taking an amino acid sequence and saying this is the shape that it's going to have in 3 dimensions. The program says, okay, here's the shape we want a protein to have. Here's an amino acid sequence that ought to be that shape when it folds up. And that is very much a qualitative step forward.
What are the practical applications of this stuff?
Oh, I mean, they are. I mean, I can't begin to do
There's lots
justice
of them.
to. It's just like it's completely transformative. I mean, what happened with AlphaFold itself was that's comparable to the impact that we had 20 odd years ago when the human genome was sequenced. It didn't necessarily make it possible to do anything that you couldn't do before, but it made it vastly easier and cheaper and quicker to do these things. Um, when we have a way to design a protein of a particular shape, then we essentially sidestep evolution. The thing about evolution is, it's discovered this thing called a protein, which has this enormous versatility. You just have these 20 amino acids, and just depending on which order you put them together, you can make this enormous variety of different things. And that's wonderful. But you can only get there in small steps because evolution only works in small steps. If you can start de novo from saying, okay, I want this shape, and crunch it up, and just get an amino acid sequence that's completely different from anything that ever evolved, then it makes the whole of drug discovery completely different than how it was.
Oh, oh dear. Oh no.